So hello, everyone. Today I'll be talking a little bit about the lunar paleomagnetic record. Whenever we want to conduct magnetic studies of the moon, we're really interested in figuring out, did the moon produce an ancient dynamo field? And if so, what were the intensity, duration, and power sources associated with that field? And the reason we care about this is that planetary magnetism can shed light into a range of other planetary processes, such as the internal thermal evolution and heat loss of the moon, mantle geodynamics of the moon, and potentially even the volatile history of the moon, since magnetic fields can control the escape of certain species. If you look at remnant crustal magnetism data observed by spacecraft magnetometers, what we see is that much of the lunar crust retains remnant magnetization. And given the ages of the crustal magnetic anomalies that have been inferred, we think this is pretty good evidence that the moon generated a dynamo at least in the period prior to about 3.9 billion years ago. But in order to understand the moon's magnetic history after 3.9 billion years ago, we really need to resort to studying paleomagnetic samples, in particular, the samples returned by the Apollo missions. And over the past couple decades, a bunch of modern paleomagnetic studies have investigated the paleo intensity history recorded in lunar samples. So each of these points here is a different Apollo sample with a different age. And on the y-axis, we're plotting the paleo intensity, or the field strength that we believe magnetized those rocks when they formed on the moon. And so there are many samples that do show evidence of ancient lunar magnetic fields and have non-zero paleo intensities. Then there's a class of samples that do not appear to contain stable magnetization in the rocks. However, this could be due to two things. One, the rock may have formed in a zero field, or alternatively, the rock may be a poor magnetic recorder and may not be capable of having records retrieved from it if the field was below a certain critical value. So that's what we plot here in red as upper limits on the field imposed by the rock's magnetic recording properties. And so over the past decade, we developed this sort of timeline of lunar paleo intensities where there was sort of a high field period where strengths were comparable to the Earth's field today, followed by a decline in field intensity. And we've inferred that the lunar dynamo probably ceased by about 1 billion years ago. A couple of years ago, there was this paper by Tarduno et al. That interestingly found that fragments from some of these older samples that in some cases have ages roughly overlapping with the high field period in lunar history did not contain a stable remnants. And this paper tried to argue that these samples recorded a zero field, but the way we interpret it is actually it places an upper limit on the field of about 2 microtesla. So it's not necessarily zero. But regardless of how you interpret this data set, it is very interesting that you might see evidence of very variable paleo intensities during the period between about 3.5 and 4 billion years ago. So we want to investigate what is causing this dichotomy in paleo intensities. Did dynamo field intensities actually fluctuate very substantially? Or did impact-generated magnetic fields magnetize some samples, perhaps those with higher paleo intensities? Or alternatively, did some moon rocks get magnetically contaminated somehow prior to paleomag analyses? So for this talk, we're going to focus on trying to assess the third possibility. Can we rule out magnetic contamination in lunar samples? And this was a possibility that was raised in 2008 by a paper by Kristen Lawrence et al. There's a few possible ways to contaminate moon rocks. One, moon rocks can be exposed to magnetic fields on the Apollo return spacecraft or during magnetic exposure to magnetic tools during sample handling. Alternatively, some moon rocks were actually cut dry using circular saws and band saws that could have heated the saw cutting surface and imparted a thermal magnetization in them. And other samples could have been remagnetized by long-term exposure to the Earth's magnetic field. Now, I will say that in nearly all modern studies, we have done a really good job of excluding the latter two possibilities by screening out samples that had dry saw-cut faces and also conducting experiments to assess how much these samples could have been magnetized by the Earth's field. And in this talk, we're going to assess this final possibility about what could happen as a result of spacecraft fields. During the Apollo era, this paper, Strangway et al., 1973, actually sent a moon rock back to the moon and back to Earth again. And based on their experiment, they concluded that moon rocks could have been exposed to fields as strong as 3 to 5 millitesla while on the Apollo return spacecraft. So we wanted to do a way more comprehensive study of this type of magnetic contamination to see how rocks acquire contamination and how easily it can be removed in paleomag studies. So we studied 6 Mare basalt samples and 2 impact melt samples, and we exposed them to a 5 millitesla field for 48 hours to give it what's called a viscous remnant magnetization. And the way we did this was we placed the sample close to a neodymium magnet and were able to expose it to this controlled field intensity. After this exposure, we removed the sample immediately, loaded it onto our magnetometer, and for a period of about an hour, we continuously monitored the viscous decay of the magnetic contamination in the sample. So what we're plotting here is the moment normalized by the initial moment versus time. And what you can see is that the rate of decay is a function of log time. So it's linear with log time. But the thing that's a little bit nerve-wracking is that our results show that it could actually take a long time for this viscous contamination to naturally decay, possibly years, depending on the sample. And so the question is, how are our paleomagnetic studies affected by this? Now, what we use in most paleomag studies is a technique called alternating field demagnetization, where we demagnetize samples using alternating magnetic fields of increasing amplitude to slowly remove magnetization from the rock. This is done at room temperature, so we don't thermochemically alter moon rocks. And so what we did was we conducted alternating field demagnetization of our contamination, and we plotted the moment lost at each alternating field step. And then we also remagnetized the sample fully in a known field, and we plotted how that magnetization was lost as a function of increasing alternating field steps. And so we plotted these 2 experiments against each other. And if there is consistent loss in magnetization, that would be an analog to reporting a paleo intensity value for a lunar sample, we would see a positive slope. And if we're not losing magnetization anymore and we've completely removed the contamination from the sample, we should see a flatlining of the slope at high alternating field steps. So what we noticed with our Mare basalt samples is that, yes, there was contamination in the rocks indicated by these positive slopes, but if you get to high demagnetization steps, we always get flatlining. We are always able to remove that contamination using alternating fields of 10 to 50 millitesla, which is pretty typical in our experiments. And that's good news because the stably magnetized basalts that have been inferred to have dynamo records have magnetization persisting to well above 10 and 50 millitesla. Here's an example of 10020, where the magnetization proceeds to over 100 millitesla. In impact melt rocks for 65035 glass and 65315 glass, we had some differing results. For 65035, we were again able to fully remove that viscous contamination, but in 65315, we had some issues and we couldn't fully remove it using AFD mag, and we were able to get a false positive paleo intensity from that particular sample. Although we note that these samples were only allowed to decay for 1 hour prior to their demagnetization experiments, whereas on a real Apollo sample, they might be allowed to decay for months in a magnetic shielded room before we start experiments. So this is like a worst case scenario. Then we conducted a second experiment to see how paleo intensity estimates are affected by contamination. We applied an analog for a 100 microtesla primary thermoremnant magnetization, which was in the form of what's called an ARM or anhistoritic remnants. And then we applied a perpendicular 10 millitesla IRM contamination. And we conducted AFD magnetization and paleointensity experiments on the resulting remnants. What we found was, again, the contamination produced a high paleointensity of several hundred to even 1,000 microtesla. But after that contamination was removed, as indicated by the yellow arrow, and then the underlying remnants is the blue arrow, we were able to successfully remove the contamination in all cases and get accurate paleointensities close to 100 microtesla for all samples. So the takeaway is that paleointensities from Apollo samples with remnants persisting above 50 millitesla demagnetization steps are likely accurate. So in conclusion, what we find is that magnetic contamination after the sample was collected can be ruled out as the origin of remnants in most Apollo sample paleomagnetic studies using room temperature demagnetization methods. That means that the lunar paleomagnetic records that we are seeing were in fact acquired from the moon. Now, in this particular study, we are not endeavoring to distinguish between the dynamo field hypothesis or the more recently proposed impact-generated magnetic field hypothesis, but we can say that we didn't do it here on Earth or in the spaceship. And what I'm going to say is some recommendations for Artemis and other future lunar sample return missions. We do need to take care during future sample return missions and subsequent handling to mitigate magnetic contamination. We recommend that rapidly cooled vitrifieric rocks and impact melt rocks that are more susceptible to viscous contamination should be allowed to decay in a zero field for a long time prior to paleomag studies. The second recommendation is a little more paleomag-niche-y, but we find that low temperature pretreatment in a zero field, heating it to about 125 degrees C, may significantly remove viscous contamination based on the magnetic properties of iron nickel. And so in an ideal scenario, we would use room temperature and partial thermal methods in tandem with each other to make sure that we're really getting a true lunar record. And then also during preliminary examination of samples, after upcoming missions, we should try to prioritize magnetic measurements so that they are conducted prior to other laboratory experiments, such as putting samples in an SEM or a microprobe that may have magnetic components or sample stages that can cause strong field exposures. So thank you very much, and I'm happy to take questions.